Some logistics before we start our last lecture today. I think you must have received at least 2 emails. One that it wasn't a surprise that the final is the last week, and it's the school time for the finals. And you must also have received another email for homework 2 and 3 combined into one homework. So I think the time is also until next week. And then I give you some extra time. I think pay attention to the due time. It is way after 12, so that, you know, if you're taking your final and you will have enough time to submit your homework. Right, anyways, just be aware of those stuff. And regarding your exam, I think now you should be familiar with our exam style. It is going to be similar to similar experience of what we had in our midterm. The same rules, the same settings, the same format. So just be prepared for it. All right. I think last week we landed over here. So this is one of the exciting moments that we are going to design a complete system together. So we start with this one, which is a naive, I will call a version of voting system. So we assume that we have some n number of voters that they want to vote on a subject as yes or no. And then we call the voters Vn to V1 to Vn. And then we said that we have a trusted sender, that this trusted sender would be the one who would set up the system, you know, set up this public board for people to, you know, cast their votes. And then we said that we assume this guy to be honest. That means that he will follow the protocol honestly, but at the same time, he will try to gain information throughout the communication. And on the top, this guy, T, trusted sender, has LGML encryption and decryption keys, where he shared his encryption keys to everybody. We denote it as encryption with T, and then decryption with T. So the votes are, we are going to use commitment scheme. So as we said, you know, this is the way that the commitment works. So before you send your commitment, we, for every voter VI, would generate a randomness RI, and then he would compute G to the RI, V to the MI, mod P, and they would send this commitment, which is their vote, to the public board. And at the same time, every voter would also encrypt this G to the RI part, only a part of this commitment, and encrypt it and send it to the trusted sender, so that only this trusted sender can understand the result of this vote. So now if you look into the public, if we multiply all these things to each other, we know that we can do that because there is a homomorphic property for commitment scheme. So we would get G to the power R1 plus R2 all the way to Rn times V to the power M1 plus M2 all the way to Mn. So this would be the results. So in order for us to now, for the user, that, you know, now that they can do this computation, in order for them to understand the sum of this M, we need to get rid of this part, right? So the G to the R1 plus R2 to the Rn. So that is the reason why we are sending this result individually encrypted under the key of the trustee, so that he can help us to, you know, do this computation, and then we can cancel out this effect. So let's see, how did we do that? So we said that, you know, LGML also has homomorphic property, so which means that if the trusted sender first multiply these things together, these pieces of encryption, so if he also multiplied these things to each other, it means that we would get, you know, the encryption under T of G to the R1 plus R2 all the way to Rn, right? If you just multiply them together. So we ask him to multiply them together first and then decrypt them. So when he does that, so we get this all pieces together, and so when we multiply them, we would get this R1 plus Rn. So we define the summation of them to be R, so we get the G to the R. And then similarly, when we multiply the commitments to each other, so we get this G to the power, I think it should be equal to G to the power R1 all the way to Rn, and then V to the power M1 plus M2 all the way Mn. So I define S to be the summation of these messages M1 to Mn. So as a result, after we multiply all these things to each other, we get G to the R, V to the S, and over here we get, after decrypting this thing, we get G to the R. So so then the final result would be, dividing the multiplication of commitments to the decryption of this part, the part that the trust center would do for us, so that we divide them by G to the R, and then the result would be V to the S. However, we discussed that, so we compute V to the S mod P. However, the question was that how do we find S from V to the S? It looked like that we need to solve this discrete logarithm problem. So yes, that is a correct way to see it. But since our number of the way that we vote was the vote was yes or no, 0 or 1, and then if everybody votes yes in a worst case, then the sum here would be n, which is the number of the voters. So at the end of the day, we have limited number of the voters. So how we can do that? We can just try to do compute V to the S from 1, 2, 3 all the way to the S, and check where this result V to the I that we are computing over here is equivalent to V to the S. And if that is the case, then we say that the I is the S that we are looking for. So essentially what we have to do is just write a for loop. And then in the worst case scenario, we will loop over n times. So of course, the number of the time that we want to iterate over it, it would be maximum polynomial time, because this computation, it can be done in all polynomial time, assuming that number of the voters are not exponential, so which is most of the time that is the case. Yeah, so that's how this simple voting scheme works. Just by using homomorphic properties, we could prepare and a simple voting system. But I think we should draw some guidelines over here. So we talked about this one, it was nice, but let's see what are the issues and how we can solve them. So the first question is that why T is assumed to be honest. We said that we need T to be honest, right? In the beginning of the protocol, we said that we assume him to be honest. The reason for this guy to be honest is that if he is not honest, and if he can do computation arbitrarily, what he can do is that he can go ahead and decrypt this piece. So when he decrypts this piece, he can recover G to the Ri, and therefore he can go and understand what this person has voted for. So let me show you here, because T can compute G to the Ri from encryption of under T, G to the Ri. And then once he has that, then T can CVI's vote by doing V to the V to the MI divided by G to the RI from the commitment. So this is actually, let me just do it correctly. CI divided by G of RI, which is going to be G to the RI, the commitment, right? And then this is going to be V of MI. And we only have two options. Either this is V0 or this is V1. So then, therefore, if our trusted center is not honest and he goes ahead and decrypt this piece of information that everybody provided, then he can actually read everybody's vote. So that is why we said that we assume he's honest, meaning that he would only follow the protocol honestly. That means that he wouldn't do this piece, this this action, but he can do that if he's not truly honest. Then the next question we can ask is that what is the overall security of the system? Is that a question? Okay, I invite everybody to mute yourself if you don't have any question. I think we have some background noise of the system, of this scheme. So looking into the security of this scheme, we are seeing that we are using commitment scheme, that the commitment scheme by itself, the hiding property is unconditionally secure, as we discussed last week. So this is a very good property. However, we are seeing that we are sending this G to the RI using Al-Gamal encryption system. So, well, it means that this would just remain hidden, the commitment, as long as G to the RI cannot be recovered. But, well, since we are sharing this one with Al-Gamal encryption system, and Al-Gamal is only computationally secure, then it means that the entire system would become, computationally secure. So our argument here would be commitment scheme has unconditional security property, but Al-Gamal is only computationally secure. And this means that our voting system, voting scheme, is only computationally secure. Okay. So I think now we understand that, okay, so the first version that we designed, it looks okay, at least we hide the results or the computation, or we keep the vote secure against some other party such as Eve. Assuming Eve is also honest but curious, meaning that he wouldn't deviate, he wouldn't change the votes, he would just try to listen to the line. He wouldn't understand the results, but we kind of have to trust this trusted center, and then it's look like to be way too much, because if he just turned to not be honest, he can read every vote. So I think today we would spend some time to see how we can fix these problems that we've just drawn over here. So before we get to solve those things, we need to learn one more piece that is something that we call it secret sharing. So in a secret sharing scheme, remember that sometimes we have a box, imagine that 3 locks. So I have lock A, lock B, and lock C. And then I think you often have seen in the movies that, at least, 2, people with these right keys for lock A or B or A or C should show up so that they will be able to open this box. So if you look at this logic over here, so we have this lock A, lock B, and lock C, and then you have user 1, user 2, and user 3. So the whole thing is that if user A and B are there with their keys, then they can open the box. If user A and C is also there, they can also open the box. Or user B and C are there, they can also open the box. So this is like sort of, schema that, we can define that at least, 2 out of n or whatever out of t out of n number of users are present, they can open the box together. So this kind of a scheme is we denote it as 2 out of 3 secret sharing. In cryptography, it also found a lot of application that you have, 3, for example, piece of secret, and then as long as 2 of those pieces of secret are there, you can recover the true secret that you want to share. So overall, the way that it works in math, if you want to formalize this one, is that you have a secret S, and then you have n users, U1, U2, U3, all the way to UN. And then you kind of chop the secret S with some method, and then you give every user a piece of that. So S1 for this one, S2, S3, all the way to Sn. The promise is that if we have then T out of n users are get together, that means that if you have user 1 and then user 3, user 5, user 6, and so on and so forth, so that user k, such that the length of these guys are t, then they can recover this S. But if there are less than t users, then there is no way for them. There should be no way for them to recover the key k, the key S. So this is like the problem that we want to solve, and this would really have a very good application for us to replace that one trusted center, and we can add multiple trusted centers. And then instead of assuming one of them to be honest, we can just assume that, T of them would be honest, and that would be enough for us to be able to recover and do all our computation. So this is the scheme that we are going to talk today, and this is how the secret sharing would be done. Is one of the ways, and it's one of the most secure ways. So the idea is that if imagine you are in a Euclidean space, and if I give you 2 points, right? Let's say I give you a point here and I give you a point over here, and I ask you how many so for every 2 points, every t points, I ask you to draw a degree t minus 1 function. So right now I give you 2 points and I ask you, can you draw a function of degree 1 that can pass through these two dots. So surprisingly, there is the answer to this is a unique. There is only one polynomial that can pass through these two lines, and that is a phenomenon that is known as polynomial interpolation. Giving you t dots, then you can plot a degree t minus 1 polynomial to pass all dots. So for example, if I give you 3 dots on this plot, so there will be only one degree 2 polynomial that can pass through them. For example, if I draw the line over here, here, and here, so you will see that there is only one polynomial, degree number 2 polynomial that can pass through there. If I let you to use degree number 3 and 4, of course, then there will be multiple, but we set it to be just, degree t minus 1. So then there will be, there is only one that you can uniquely find this one polynomial that can pass through this point. So this is the idea. Just keep this one in mind, and let's see how we can design this scheme out of this observation that we've just discussed it together. So the idea over here is that when you want to have t out of n secret sharing, so the requirement is to have this setup. So we need to find a degree t minus 1 degree polynomial. So we are going to denote this polynomial something like this one. So this polynomial f of x is going to look like bt minus 1 xt minus 1 plus bt minus 2 xt minus 2 all the way to b1 x to the 1 plus, and then it says that the secret that you want to share among every user, you're going to just put it at the end. So you have some polynomial that the degree 0 variable over here is just the secret that you want to share, and this is going to be mod q, right? And every bi over here is an element from zq, and from 1 to q minus 1. So those are the value bi's. So it says that you're going to go and randomly find these bi's, and then you just form this function. And then you're going to insert your secret key at the last element. And this is now we are ready to start to utilize this system. And then the second thing that it is asking us is that for every user that we have in our system, we are going to give some share of the secret key to every user, and this share for every user I would be xi and yi, right? So it says that so you have user 1, you have user 2, you have all the way to user n, and it says that suppose this is our polynomial that we have just created. This is suppose f of x. Of course, it is mod q. We cannot really plot it. It would be basically some dots. But let's just imagine that we can make it. We just plot it. So for user I, it says that for user 1, just compute 1 and f of 1, 2 and f of 2, and so on and so forth, and f of n. So if I'm computing, this is I, so then I'm computing the f of I, and that will be the piece of share for this user I over here. So again, you see that we embed our secret s into our polynomial. So by combining these pieces, and basically we are giving every user a dot, right? A point on this Euclidean distance space, And now the point is like if T of them get together, then we can reconstruct this degree T-1 polynomial, and then we can therefore recover this S. So that is what we are talking about. So given that, so now we don't know the polynomial, now the setup is finished. So imagine that later on, T user get together. So we would have T different points. And this is how we can reconstruct according to the Lagrange polynomial interpolation formula. But we don't want to go through the proof. This is just what we want to take it as a fact, that this is how you reconstruct this function f of x using only these t points. And so it is going to look like some formula, some summation over every of this, f of xi's. If I call this one xi and this is yi, if this is the format. So we are going to do this sort of computation. So I'm going to call this piece over here, we also call it lambda I. So after we do all this computation, but don't worry about it, we will go through the details. So I'm able to compute the function f of x. And looking into this function, if I compute f of 0 over here, I constructed this function, meaning that I know all this, coefficients. If I compute f of 0, then it means that the output would be s mod q. And that means that, after I reconstruct this function f out of these t points, I compute f of 0, then I just basically get the secret that I was looking for. So let's see how this actually works. So when T users get together, so we would have x1, let's say y1, I don't know, x3 and y3, and so on and so forth, up to t of them, xt and yt. Then where this length of this guys are t, then we can do this computation. So the first thing that I want to discuss is how to compute this lambda I. It looked like a little bit weird over here. So let me define this lambda I. This lambda I is basically, it is going to be multiplication some huge number. So for the case of the easiness, let me just say exactly the first T users will show up so that or indexing here becomes correct. So there could be different combination of them, but we need T of them. But let's say we index them from 1 to T, and exactly user 1 to T show up. Then for lambda I, according to the Lagrange interpolation formula, we have to do this computation. So we need to have x minus x1, x minus x2, x minus x3, all the way to x minus xi minus 1 times x minus xi plus 1, all the way to x minus xt. So if you notice, for when we are computing the lambda of I, the point I, we do this formula variable x minus every other point except the i's point. And then here, the i's x come to play, xi minus x1, xi minus x2, again, we won't, let me just make it clear over here. Okay, so basically every time that we are computing this variable lambda I, we would plug in every point that we have from here, except we won't utilize the ith point. And you see that on the top, we would just skip the ice point. And on the bottom, if we do xi minus xi, it would be 0. So it would make everything to be 0. And we would just skip that one. So the idea is that, so this is just this one computation, and you see that we have a summation of them. So the idea is that basically we can recover the function x by computing lambda 1 of f of x1 plus lambda 2 of f of x2 plus all the way to lambda t of f of xt. And then once we recover this f, then we compute f of 0, which would output s for us. Let's see this one with an example. I think that should be able to make it easier to understand. So, example. So suppose I choose a polynomial that my polynomial is f of x equals to, let me choose a small one, x2 plus b1 x plus, some s mod p mod q. So suppose this is my polynomial, and I don't really need to have exact values for b1s and s. So I compute the 3 secrets out of this. So I want to have 3 out of n secret sharing scheme. So I would say x1 and y1, I need to have x2 and y2, and I need to have x3 and y3. Okay. So we would basically continue this one for n users, but let me xn yn. So suppose that after we plug in this, the value we get is 1 and 5. So when I compute f of 1, I get 5. Compute f of 2, I get 3. I compute f of 3, I get, let's say, 7. And so on and so forth. So according to this formula, I can recover this function f of x by having 3 points over here. And the recovery would be y1 times this lambda terms, that when I'm computing using this one, I will get x minus 2 and then x minus 3, right? We don't play with this xi that we have over here. And then I would have 1 minus 2. And then I would have 1 minus 3. Plus, we go with the y2, so we have y2. And then we have x minus x1. And then I can do x minus x2. I do x minus x3, x minus 3. The reason I don't do 2 because we are computing lambda of 2, and according to our formula, we should skip that ice index. So, and then I get 2, and then now I have this one, minus 1, and then I compute 2 minus 3. And then plus another y3, and the same logic I follow, so I get x minus 1, I get x minus 2, so I get 3 minus 1, and then 3 minus 2. So also I know the y1, y2, and y3. So the y1 is 5, y2 is 3, and y3 is 7. So when I plug all these things, I can reconstruct the function f, and then all I need to recover to know the secret is to compute f of 0, right? And so f of 0 would become what? Would become, so if I replace every x over here with 0, so I'll get 5 times minus 2 times minus 3, over 1 minus 2, 1 minus 3, plus what is 3 times minus 1 minus 3, 2 minus 1,
2 minus 3 plus 7 times minus 1 minus 2, right? So after that, I can compute just f of 0, which is going to be my s mod q, right? And that's how I have recovered my function, my secret s that I was looking for. So all I have to do is, again, going back to the same idea, that if I have 2 points, I can uniquely construct one polynomial degree 1 that can pass through both of these points. And if I get 3 points, then there is only one degree number 2 polynomial that can pass through all these points. So given t points, I can uniquely construct one degree t minus 1 polynomial that can pass through all those t lines, and therefore I can reconstruct that function. But the idea is that if you don't have t points, let's say I have all the points all the way to t minus 1, then there is no way, if I don't know that last point, to be able to construct that degree t plus 1 point. There would be infinitely many polynomials that can pass the t minus 2 points, and then the last point would be variable, right? Because I don't know. Then there would be infinitely different polynomials that I can imagine that I can draw, but there's no way that I can uniquely identify that specific polynomial f of x that I am looking for. So therefore, we wouldn't be able to reconstruct that function over here. So this is a very interesting result, and it found a lot of different applications. You don't have to use it in the voting system. You can imagine that if you have access system, you want to let the users to get access to the files. You can have them to share the key, and if 2 or 3 users show up, they can recover the key of the AES, for example, and then they can decrypt the file. Or if less than t of them show up, then they wouldn't be able to recover the key. Therefore, they wouldn't be able to decrypt the file. So the same system you could utilize for different purposes. All right, going back to our election system. So now that we know that we didn't like the idea of having one trusted center, to be honest, one of the ways that we can get rid of that is to replace that one authority, that trusted center, with n different authorities. So, so the idea here is that what we are suggesting is that we want to replace t with n authorities, and hoping that t out of that n authorities are honest. The rest of them could be hackers, they could be bad players, that they would do arbitrarily wrong computation. As long as t out of n of those authorities are honest, then then we will be able to continue with our election system confidently that the results are correct. But that means that if we have t honest authorities, then we can recover the secret and count the votes, right? So this is the idea right now. So this is always one of the tricks, so that you don't want to trust to one person. So you sort of distribute that trust among n players, and we only hope that you know, t out of those n are happen to be honest, then the system would work. But of course, if you can get that satisfaction that t out of that n party would be honest, then you will have serious issues. So there are also workaround around there. So that is one of the ways that the number n authorities, you know, that is one of the ways that we define n. If you feel like that, you know, the chances of attacker are also high, so you want to continue with more n, increase the authorities by dropping in more honest ones, and hoping that if out there are some attackers that they can join as authority and they deviate, at least their numbers would always be less than honest authorities, and you know, your system would work. But of course, we would have our ways to even identify those dishonest verified authorities if there are any in our system. So the voting, we are going to change it a little bit. So for message yes, we are going to use +1, and then for -1 is going to represent a no instead of 0 and 1. We play with +1 and -1 on this new scheme that we are going to build. All right, so this is how our setup would look like now. So again, we are talking that there is a trusted sender T, but however, let me write this one later. So we have the dealer T that, you know, still we need him to set up the system, find a prime, you know, set up this function. But later I will show you how we can get rid of this one trusted sender T, and we can collaboratively create this thing. So for now, let's assume we have T to set up the system for us. Later, we show okay, so later we will discuss how we can remove this T. And basically our authorities can collaboratively construct these values for us. But for now, let's just make things simple and assume that we have this T that would set up our system. So when we talk about setting up the system, I think we want him to find a prime number, large prime number that has this format. And so we find a generator of of group ZQ. And then we also want him to choose a secret S that is a member of ZQ, and also a degree T-1 polynomial. So we know how we set up this polynomial now. All we have to do is to find its coefficients in ZQ, and with f of 0 to be equal to s, right? So essentially what we are looking for is to construct this function x, which is equals to a to the T-1. Do I use a, or okay, it's okay. Right, their AIs are member of ZQ. Okay, so he would set up this polynomial, and then he would start to compute this value. So he let h equals to g to the s mod p, of course. All this computation, they got mod p. And then we distribute the shares among the end users. So for example, for authority number 2, we are going to give him a piece of this share, which is a point, which is 2 and f of this 2, right? which is going to be his share, that we call it 2 and S of 2. So normally, remember, we would have different notations a little bit. So for user 2, authority 2, we compute 2 and F of 2. So we already have our F function. And then his share, we're going to call it 2 and S2, or secret of for user 2. And also we are going to compute his public key to be H of 2 equals to G to the power S2 mod Q mod P. Okay. So at the end, you will see that at the end, you will see, let me just be a bit more generic over here, maybe. So AI, I, and F of I. So at the end, what I would have is that A1 has its share 1 and S1. A2 would get its share as 2 and S2, and all the way to AN, which would have its share of N and Sn. And then also for every of them, we compute this value H1 equals to G to the power S1, H2 equals to G to the power S2, and Hn equals to G to the power Sn. Right? And then, so now sort of our system is ready. So we have computed all the information that we wanted to pre-compute. Now we are ready to set up the system by publishing these values as our public key for the users to come and utilize our system. Okay, so maybe this is the perfect time to get some break time, and we would come back at 9 o'clock to continue our class.